So we're moving into discussing Kepler's laws themselves. Now when we refer to Kepler's laws, we refer to them in a very similar way as we refer to Newton's laws. There are once again three basic laws, and only one of them has a calculation. And these really dictate how objects move in stable orbits. So, any planet, as it moves around in its orbit, is actually not going to be moving in a perfect circle. And we've already discussed the kind of geometry we should expect to find in an orbit. And Kepler's first law really makes a statement that no planet is in a particularly perfect circular orbit. So Earth's orbit, as I said, is very close to circular, but still not quite circular. That means as a planet moves around in its orbit, it's progressively further away from the Sun at one end of its orbit and closer to the Sun at the other end. We call this, if we're looking at the Sun system, perihelion when a planet is closest to the Sun, and aphelion when a planet is furthest away from the Sun. Now this applies to any orbiting body, so if we're talking about something orbiting the Earth in an ellipse, you end up with perigee being the closest approach and apogee being the furthest approach. If you're talking about Mars, it actually becomes apoair and periair because they decide to go for a option of looking at Aries instead of Mars. Personally, periair sounds like a brand of spring water. So when a planet moves in an ellipse, we can define a couple of things. One, a major axis, which is the long axis of the orbit. The minor axis being the shorter axis, the perihelion, and the aphelion. And Kepler's first law really just made the statement that planets move in ellipses, and the orbit of each planet is an ellipse with the Sun at one focus. The other focus is located in space. And we saw this previously when we talked about perfect circles and ellipses. If we were looking at a perfect circle, the Sun was at the center and the body went around it with just a singular radius. Same as a perfect circle around the Earth. You would have the body moving around the Earth with the Earth at the center of the radius. When we are looking at an ellipse, there are two foci or focus points to that ellipse, and the Sun sits at one of these. This means the distance from the Sun to the planet varies. As I said, this could be a planet that we're orbiting, but I'm going to use the Sun as a main example. Now, if we look at our solar system, a great example of this is something like Mars. Mars has quite an elliptical orbit, and actually its distance from the Sun varies between 19% between aphelion and perihelion approaches. So again, here's our geometry. Here's the planet going around the Sun. We can define a semi-major axis and a semi-minor axis, and a close approach and a furthest approach. Perihelion and aphelion. And there's the eccentricity of some of the orbits, how far away from circular they are. We have to be kind of nice to Mercury. It's right next to the Sun, and as such, it can only be explained using general relativity because of the high gravitational field it happens to be within. We've got Venus, quite well behaved, quite circular. Earth, very circular. This is 0.01 or 0.02 here compared to 0.06 for Venus. Mars, like I said, almost 0.1. This is quite an elliptical orbit for this body. Jupiter, not too bad. Saturn again, Uranus. Neptune, very well behaved. Neptune here. And Pluto, again, this is a bit of an outlier because Pluto is actually quite an inclined orbit and quite an eccentric orbit. One of the reasons Pluto has been kicked out of the Planet Club of late. And one of the things we can do using orbital mechanics and looking at the ellipse itself is define the distance from furthest approach and closest approach, the aphelion and perihelion distance. And these are relatively easy to do in these terms that the perihelion distance, which is given as RP, and the aphelion distance is given as RA, is just A, which is the semi-major axis of the orbit, times 1 minus E for perihelion and 1 plus E for the aphelion. So we could say here, what's the variation of of Mars's distance from the Sun? For Mars's orbit, the semi-major axis is 1.5 AU. Its eccentricity is 0.0934. If you're doing a calculation like this, always use A in astronomical units and P in years with Kepler's laws. That being said, the astronomical unit is the distance from the Earth to the Sun. So everything defined as 1 being the distance from the Earth to the Sun, and then everything else defined as a fraction of that. So Mars here is about 1.5 times further away from the Sun than we are. So if we look at that, there's our geometry, there's our planet, there's our axes. So RP here will be A, 1 minus E. This will be 1.5 times 1 minus 0.093. That'll give us 1.3814 AU. In terms of aphelion, do it again, the only difference being 1 plus E this time, and we'll get an answer of 1.666 astronomical units. That's a difference, if we take the difference between these, of 0.22846 AU. And that's quite a lot. It's about 19%. And there's Tycho, showing these kinds of things to Rudolf II. This was, of course, Kepler's boss, trying to explain these things. Because of these 19% variations that we see in the orbit, we end up with a situation where the seasons on Mars are quite extreme. Combine the actual distance from the Sun varying so significantly with an axial tilt of about 25 degrees, and you have a situation where you have very extreme summers and very extreme winters, especially in the southern hemisphere, I should say. And there's the polar cap regression, the kind of thing we see, the polar caps of Mars changing significantly over the course of a year due to these orbital effects. So, when we're looking at these situations, we're not so bothered about what's going on in terms of ellipses. What we really care about is what's going on in terms of the physical mechanics here. What's going on in terms of the physics? And Newtonian theory combined with Kepler's law answered a lot of questions. And we can look at this in terms of energy and energy transfers. So when we dropped a ball down a hill, we could take the gravitational potential energy and convert that into kinetic energy. And that's essentially what we're doing in the case of these orbits. So when we're over here in our orbit, we have more kinetic energy. When we're over here, we have more potential energy. When the distance is a maximum, potential energy is maximized. When the distance is a minimum, kinetic energy is maximized. That was Kepler's first law. Kepler's second law, which was done without the benefit of Newtonian gravity, makes a statement that the line drawn from a planet to the Sun sweeps out equal areas in equal times. What he was actually saying is when a planet is further from the Sun, it moves more slowly. When a planet is closer to the Sun, it moves more quickly. So Kepler was figuring this out without the benefits of mechanics, as I said. And what he noticed was, if a planet here moves from point A to point B, and then in point C to point D, the area of each of these segments of the circle will end up being the same. This is a short, wide area. This is a long, narrow area. But area 1 is equal to area 2. And so he said that the area swept out will be equal time. So that means that over here, the planet is moving faster. Over here, the planet is moving slower. So at perihelion, we have more kinetic energy, so a higher velocity. At aphelion, we have a lower kinetic energy and a greater gravitational potential energy due to the distance from the Sun. And if we actually look at the average orbital speed of the planets, this works out quite nicely. Here's Mercury, Venus, Earth, Mars, Jupiter, and Saturn. This is distance, and this is their average orbital speed. And there, just because we've been discussing eccentricities of orbits, we can see them all together. So something like Comet Halley here, here's Halley's Comet, has a massive variation in its speed. It spends a long time out here in the extremities of its orbit, but moves very, very quickly as it's coming past the Sun, and indeed picks up speed as it approaches. And there's just a reminder of those eccentricities. So when we're looking at orbits, there's some orbits that are advantageous, especially if we're building spacecraft, and others that are not so much. And if we want to look at efficient ways of boosting things to other planets, then we do have to abide by the inverse square law and think about elliptical orbits and how our velocities will vary. So here we have the Earth, and here we have a satellite going around the Earth. In this perfectly circular orbit, there will be no variation in velocity. It'll be in a constant potential. The equation for our orbit will be kinetic term plus a potential term will be constant. In the case of this orbit, this more extreme orbit here, we'll see a situation where we have a perigee, a close approach, and an apogee, a furthest approach. And from what we've just said, you should be able to surmise that we'll have a high velocity here and a low velocity here. And if we're sending spacecraft to something like the Moon, that means we have to take these things into account. And there's the Apollo 8 lunar orbital plan profile. This is from one of my original documents, hence the grainy quality. But the Saturn V would take off, go into orbit around the Earth, and then fire its engines and do what it was suggested as a translunar trajectory. Over here, you actually have a lunar injection, as it's referred to, where you essentially start accelerating due to the gravitational attraction of the Moon. So as you go from one orbit to the next, you can lose you'll gain gravitational potential of the Moon and lose the gravitational potential of the Earth, but be gaining velocity over here and losing velocity as you're approaching. So let's take a look at a situation where we're looking at the Moon. Here's the lunar module that people landed on the Moon with. Where will be the maximum velocity of the lunar module, and where will be the maximum potential energy? If the spacecraft goes in an elliptical orbit like this, we have a distance of 60 kilometers from the surface of the Moon here and 120 over here. Of course, we could add the radius of the Moon and look at the separation of the center of mass if we wished. But that means kinetic energy is a maximum here, and gravitational potential energy is a maximum here. That means the lunar module is moving more slowly here and more quickly here. If kinetic energy is a maximum, half of mv squared is higher, is maximized. Over here, gmm over r is maximized. And that leads us into the third of Kepler's laws. And as I said, this is the only one that has an equation associated with it. And that equation essentially is p squared equals a cubed. If you use the raw form of this equation as p squared equals a cubed, then you should really use the semi-major axis in astronomical units and the period in years. And what this is saying is the period of a planet is the time it takes to start in one position, go all the way around, say, the Sun, and come back to its original position. That's the period. A is the semi-major axis, so p squared, the period, equals a cubed. The year length equals essentially the radius of the orbit. And if you plot p squared equals a cubed, you get a beautifully linear relationship. So here we are down here with the inner planets all the way out to Saturn. You notice we only go as far as Saturn in order for this scale to actually work, because the distances between the planets are so immense. So the whole of Mercury, Venus, Earth and Mars actually fits in that tiny little square down there. This is the period squared. This is the average distance, or the semi-major axis cubed in astronomical units. So let's say we find a planet orbiting another star, and imaging tells us, so we took a picture of it and we found out that the semi-major axis is 4 astronomical units. If that's the case, what will be the orbital period of the planet? Well, p squared equals a cubed, and we're going to use astronomical units, and we're going to use get p in years. Relatively simple. P squared equals a cubed, so p is the square root of a cubed, which will give us the root of 64, which is 8. So here, the orbital period will come out as 8 years. And that calculation will work for any orbiting body. A planet, a moon, a satellite, something going around the Earth, something going around the moon, something going around the sun, any regular orbiting body. In this form, though, only use astronomical units and p in years. There is an alternate version, and we've been talking a lot about Newtonian mechanics and trying to put them in the same context as Kepler's laws, and that's really what we want to do here. We can take Kepler's laws, where p squared was basically equal to a cubed, and we made the assumption that k was equal to 1. That was a constant that made p squared equals a cubed work. Once Newtonian physics had been discovered, we no longer had to do everything in terms of years and astronomical units, and could actually get accurate values in meters and seconds. And that means taking that k value and substituting in and ending up with something from Newtonian mechanics. And that means if we combine Newton's theories with Kepler's, we get this. P squared is now equal to 4 pi squared, this is to take into account the spherical nature of the planet, over g m1, or of the orbit I should say, over g, this is our gravitational constant, times m1 plus m2, this would be, say, the mass of the sun and mass of the Earth if we're dealing with the Earth, times a cubed, the semi-major axis cubed. So for the sun and the Earth, p squared would equal 4 pi squared over g m sun plus m Earth times a cubed. And one of the things we can often do, and this is a trick that enables us to calculate the mass of a lot of things that we see with objects in orbit around them, is figure out the mass of objects that are being orbited or orbiting objects. In the case of the sun and the Earth, we could say m sun is much, much bigger than m Earth. The mass of the sun is a lot bigger than the Earth. The mass of the sun is 2 times 10 to the 30 kilograms. It's huge. So the mass of the Earth can be considered negligible in most cases when we're dealing with another star. In this particular case, in this version, if you use this version, make sure your masses are in kilograms. That means A here has to be done in meters, and P here has to be done in years. If you are using the Newtonian version of Kepler's third law, you need to use meters and seconds. I apologize. That should be meters and seconds. This is in years. So let's take a look at this as a problem. So when the Apollo lunar modules orbited the moon, they were initially placed in a relatively low orbit of about 60 kilometers. If the lunar module, the LEM, the lander that people use to go to land on the surface of the moon, had a mass of 14.7 times 10 to the 3 kilograms, calculate the orbital period of the LEM. So our data is, we've got a 60 kilometer radius orbit, a mass of 14 times 10 to the 3 kilograms, and we want to find the orbital period. So let's say we have to look up a few things here. So first, what's the radius of the moon? Here the radius of the moon is 1,737.4 kilometers. You can look this up. This is essentially 1,737 times 10 to the 3 meters. The orbit is 60 kilometers, so we have to add this together. So it's the separations of the centers of mass that we care about. We're not going to add that few meters on for the centre of the lunar module when we're already considering the radius of the moon, for instance. So this will give us 1.797 times 10 to the 6 meters going from the centre of the moon all the way out to the lunar module. That gives us about 1.8 times 10 to the 6 meters. Now applying our equation, t is equal to 4 pi squared r cubed over gm rooted. This is our Newtonian version of Kepler's law. We're ignoring the mass of the lunar module. Adding that on is kind of irrelevant. The mass of the lunar module, when we compare it to the mass of the moon, is going to be incredibly small and make next to no difference. So if we substitute in, here's the mass of the moon now substituted in, 7.36 times 10 to the 22. I would of course give you this if you were doing this as an exam problem or a class problem. Here I just looked it up. So this is 4 pi squared. Here's the radius of the orbit cubed over 6.67 times 10 to the minus 11, our gravitational constant, times 7.36 times 10 to the 22 rooted. That'll give us 2.3 times 10 to the 22, or 4.9 times 10 to the 12. Take the square root, and we'll end up with 6,848.45 seconds. And as per the small mistake in the previous slide, the answer from this set of equations will come out in seconds. If you're using the Newtonian version, you will get an answer in seconds, and you'll put your variables in meters. So, to make this a little more informative, because I don't really think well in terms of 6,800 seconds, let's convert to hours and say 6,848.45 over 3,600, that's 60 times 60, 60 minutes by 60 seconds, will give us about 1.9 hours, or about 2 hours. So this is actually accurate, and you can actually look that particular value up in anything to do with Apollo. Let's take a look at another one. The average distance of the Earth from the Sun is about 1.5 times 10 to the 11 meters. The orbital period of the Earth is, a year, with 365.25 days. If we multiply that up, 365 days, we've got 24 hours, we've got 60 minutes in each of those hours, and we've got 60 seconds. That gives you about 3 times 10 to the 7 seconds per year. Let's calculate the mass of the Sun. And this is a calculation that people actually did once they were armed with this equation, and it changed the scale of our entire solar system. So p squared is equal to 4 pi squared over g m1 plus m2 times a cubed. m2, of course, is negligible. We're dealing with the Earth and the Sun. So rearrange, get rid of one of the m's, and we end up with m being 4 pi squared a cubed over g p squared. Let's make some substitutions. Here we can substitute in, this is our A, this is our G, and here is our P. It's going to give us 4 pi squared times 3.34 times 10 to the 23 here over 66.6 times 10 to the third. This will give us about 2 times 10 to the 30 kilograms. That's about what we would expect. 10 to the 33 here. That'll give us 2 times 10 to the 30. That is the value of the mass of the Sun. So just to finish up our discussion on gravity, there's a few other things gravity does. As the moon is moving around the Earth, it actually pulls on the Earth and deforms it a little bit. The tides that we experience on the Earth, sometimes people think it's the moon pulling on the water. That's incorrect. It's actually the moon pulling on the Earth and deforming the planet a little bit. And then essentially as the moon rotates, it actually keeps that deformation towards it and ends up sloshing the water around on the Earth, a bit like the water in a cup. And that's why we have tides that follow the phase of the moon. Nothing to do with the moon pulling on the water. Due to tidal friction, the Earth's rotation is actually slowing a bit, and the moon is actually getting further from the Earth. The moon once orbited us much faster. Also, the rate at which the moon rotates is also on the order of the rate at which it orbits the Earth. Therefore, we only ever really see one side of the moon. Some things gravity cannot explain yet. Our current gravitational theories, if we follow them, say that if we look at something like a galaxy, as we get further from the center of that galaxy, we should see the rotation speed of stars in a galaxy fall off, following Kepler's laws. And as we know, Kepler's laws work beautifully inside the solar system. Outside of the solar system, if we are looking at a galaxy, then what we actually see is that the galactic rotation curve does not follow Kepler's laws and actually flattens off at large radii. This is actually an example of dark matter or dark energy that people are talking about, and at very large distances this dark energy has to be accounted for and taken into our calculations to explain why galaxies don't come flying apart. And finally, no discussion of gravity and gravitation is complete without mentioning black holes. This is about as extreme as we can get where gravity is concerned. In fact, they're gravitational singularities, and you end up with a situation where the gravitational force is so high that the escape velocity approaches 3 times 10 to the 8. That's the speed of light. So light cannot escape from a black hole because its escape velocity is so massively high. Just to be a bit weird, because we're dealing with relativity, we have a situation where time actually slows down at the center of a black hole or near to the center of a black hole, given the fact that general relativity is actually taking over instead of Newtonian physics. That means anybody who likes black holes might be a bit disappointed because you can never get a perfect singularity, because you can end up with a situation where it takes an infinite amount of time to form an infinitely massive body. Therefore, you get something that's 99.9% of being a black hole, but it's never actually a perfect black hole. And there's the typical diagrams that you see where space is being distorted by an enormous mass. So this essentially is a map of local space, time, and gravity. So very high gravitational fields can disrupt space and time. So one of the things about black holes I often get asked is, it's a black hole, it's black, space, it's black, how are you supposed to see them? Well, we can look for gravitational lensing, which I'll talk about next, or we can look for material spiraling into a black hole, which tends to get backed up in a traffic jam, and friction makes this extremely hot. So they show up nicely in the X-ray. Finally, if we are looking at distortion of space and time by enormous masses, you can actually have an effect called gravitational lensing. And that's where space is so distorted by a supermassive object that light actually bends around it and follows a path around the object rather than being blocked by it. And this has the effect of forming multiple images of the same object in a ring around these highly massive objects, unless you're at their focal length, in which case you don't see them at all. And this is the kind of thing we're talking about. Here we have a star, a source, something we're looking at. Here we have us on the Earth, and what will happen is light will bend around this black hole on its journey towards us. What does that mean we see? We'll see a cross pattern, or what's referred to as an Einstein ring. The same image of that object 4 times around the edge of the black hole. And this is something we actually see in galaxy clusters all over the universe. Here's one in Abell 2218. This is a very large galaxy cluster with a massive amount of gravity, and what you can see here is these lines represent the same galaxies from behind the cluster. You can see it's almost shown as like a bubble. These galaxies aren't really here, they're actually behind this object, and the light from them is bending around this enormous galactic cluster. It's a very interesting effect here. We shouldn't even really be able to see these things. So that's the conclusion of our talk on gravity and Kepler's laws.